Hey, welcome to my 7th Stickman Physics lesson. We're on 2D non-projectile motions. We're going to learn how to describe and determine vector components, put them together. We'll know the difference between 1D and 2D motion now that we've had 1D motion in the last unit. What the difference is now we'll see. Also, we'll have projectile motion with just non-projectile motion. We're going to start with non-projectile motion. We're going to be able to draw vectors when we're adding them together. We're going to learn about the head-to-tail method. And then we'll be able to name the direction and draw the direction of a 2D vector. And then we'll finish off by resolving the 2D vector for its components. Okay, so the first question is, what's the difference between 1 and 2D motion? If you take a look at these animations, you can see right here, 1D motion, you're just going back and forth in one plane. So it could be along the x-axis as you see here, or it could be along the y-axis, but you're not doing both. Whereas 2D motion, you're going all over the place. You're going along the y-axis, you're going at angles, you're doing a bunch of different things. So we're including a second dimension. What's the difference between non-projectile and projectile 2D motion? If you take a look right here, in non-projectile, the stick man, he's walking, he's running around. He's not actually flying through the air or throwing something through the air. So we'll go into horizontal launch projectile motion where you just throw something straight ahead, and the angular launch. But as soon as that ball enters the air, you have the force of gravity acting upon it, accelerating it downwards towards the ground. Whereas what we're going to start off with, it has nothing to do with something falling through the sky. That's the main difference. Okay, so just a reminder, scalars have a magnitude, which was just a number in a unit, and vectors are going to have a direction on top of it. So here are some common ones. Displacement 5 meters north, velocity 5 meters per second north, acceleration 5 meters per second, or per second squared north, but they're all going to have the magnitude and the direction. So we use arrows often to represent these the magnitude and a direction for a vector, because the size of it is going to be the magnitude, like 5 meters here, whereas the arrow tip is going to tell me what direction it's actually facing. So I'm physically going from one spot to another. And just talking about what this is, an arrow has a tail. Well, when I say tail, we're going to talk about the end where you started. And then we're going to go all the way over here to the head, and the head's going to have the direction. This is going to be where you end. And we're going to use this thing called head-to-tail method to draw vectors and add vectors together. So we're going to start, let's just talk a little bit more about scale. It's important to be able to see and visualize your answer before you type things into a calculator. So you want to have the arrows to relative scale, but they don't just have to be meters. They can be meters per second. It could be velocity. It's not always just going to be a displacement. It could be any vector, anything that's a vector can be added with arrows. Don't mix vectors. 20 meters per second and 12 meters. These would be two different vectors. Would be two different problems. We wouldn't want to put one next to the other. So likes with likes. And just drawing vector addition head to tail. We're going to start off with easy 1D motion, which we've done a little bit of before. You walk 10 meters north, followed by 5 meters north. What is your overall displacement? So we're going to start off, and anytime you do a problem like this, draw an origin dot. You're just going to draw a dot. You don't have to label origin. You're just going to go ahead and you're going to just scribble a little in one place. And you're going to start there, and then from there, next step is you're going to add your first vector. And just the best thing to do right now is just to add the first one you see. So you can be consistent with my work, so you can check your work with my work. I see 10 meters north first, so I put 10 meters north first. So I go ahead, I draw that dot, I draw that arrow, and that's my first vector. Right now we are here. Don't leave your you shouldn't even leave the paper. Right now you just went 10 meters forward. Now you're at this spot. And now we're going to add the second vector. We went 5 meters north as well. And label it, put it down the side. And now we just went, this is called head to tail. If you take a look at the head of the last arrow, the tail of the new arrow, or the next direction I go, starts from the end of the head of the previous one. And now the resultant is the overall. So when I take a look, if I went 5 meters forward and 10 meters forward and 5 meters forward, I'm going to end up getting, going 15 meters forward. In this case, forward was north. So we're just adding them together. And all you would do for resultant is maybe draw something. If it was a 1D motion resultant, just draw another line somewhere next to the first line. Try to make it as straight as possible. Maybe label that 15. That's what I would do. We're going to use these. It's going to be a lot more practical as we get into 2D motion. Once again, this is still 1D motion, but we're just about to start the 2D motion. Another thing to note is don't get over concerned with which vector you add first. So I always want you to add the first one you see first, because I want you to be able to check your work with my work. But we're going to have the same end answer no matter what you do. And so here, I went ahead and just put the 5 meters first here on this side, and I put the 10 meters first on that side. And then I went ahead and added the second one. If you take a look at the resultants. They're both going to be the same. They're both going to be 15 meters north. It didn't matter which one I did first, which one I did second. When we added them together, it ended up being the same answer. And the same thing's going to happen in 2D motion. If you follow all the directions, it doesn't matter what direction you follow first, you're going to end up in the same spot at the very end. Okay, so you fly 20 meters north into a wind that's blowing 5 meters per second to the south. Once again, review of a previous unit. We go ahead and draw that first line. We label it 20 meters per second because we're going north of velocity, but the wind's blowing backwards. So you're going to start at the head to tail, so the tail of this next arrow, and you could draw it, I would draw it on top, but then it might be hard to see. So I just drew it to the side. You're going back 5 meters per second. You're not really going back. You're slowing down by 5 meters per second because it's a velocity. And then your resultant, you go start at the beginning and you draw it to the very end, and you'll find out that this ends up being 15 meters per second north. So this is going to be the result, which is the overall. Just a reminder, because we're going to have to do this still here and there in the 2D motion parts. We're going to have to put X components and Y components together. Never, we're going to find out how to do it when you have two axes, but this is back to 1D motion. So this is just a Y axis right here. We had 20 meters per second north. We're plus 20 plus being a placeholder for north. And we had 5 meters per second south minus being a placeholder for south. And we went ahead and added the vectors. Once again, it's not always adding. We ended up subtracting because one was a different direction. And we got a positive 15, keeping the sign because the sign is going to have to turn back into a direction. So you drop the sign and you include what the positive meant in the first place. And since we were looking at north and south, positive meant north. We won't confuse it with east because we're going to do a different type of, we're going to use a little trigonometry when it comes down to 2D motion later on. So this is what we're going to get into. We're going to find a way to put 5 meters per second to the north, or 20 meters per second west, and then 5 meters per second north, and coming up with this overall resultant. That's going to be our next lesson. Right now we're going to look at breaking some sort of overall resultant at an angle into its components, its parts. This one right here would have a x-axis, 20 meters per second. This one would have a y-axis, 5 meters per second, just the way I put them together. Another thing you should know, if I could put these two vectors, once again, this 10 meters and this 6 meters, these are two separate vectors. If I want to put them in any placement, head to tail, once again, head to tail, one will have to end where the next one begins. If I will have them going the same direction, so take a look, when 10 and 6 are in the same direction, you get 16 meters. Whereas when I have them going opposite directions, I get a minimum distance, which would be 4 meters. Once again, if I could put them anywhere, depending on how I laid them down, right now this would be 16 meters east, and this one would be 4 meters east. But in general, they go the same direction. You add them together, you get the maximum, and if you have them going the opposite directions, you're going to get the minimum, subtracting the smaller one from the bigger one. So if you add them together, you get 16. If you subtract them, so maximum, same direction. There's just what I was talking about earlier. If I put them both east, that works. 16 meters east. Minimum, you're going to get them in opposite direction. So if I've laid 10 meters, one east, and I would lay the 6 meters, one west, I'm going to get this one is going to be, ignore that. It should not be plus 16. It should be just, it would have been plus 4, which ends up being 4 meters east. Okay, what's the minimum length of 125 meters? The minimum I could have, the distance I could overall from the start. Once again, this is a displacement. What's the minimum displacement? So go ahead, take a second, pause the video, answer these questions, and then come back and hit play. So the minimum is going to be 75 meters. 100 minus 25 is 75. If I want to get a maximum, I'm going to put them in the same direction, and we're going to get 125. So once again, if I'm drawing these, just get used to practice drawing them. 100 this way, 25 meters this way. That's going to be the minimum from start to finish. This would end up being my resultant. Whereas here, if I go 100 and I go 25, I have this overall resultant of 125 meters. And so that's what you're answering in this question right here. Okay, get the maximum displacement, they're going to be in the same direction. So just like this that you saw right here. Okay, and then now we're going to have to look at naming directions. This is important because if I just say go 15 degrees, you're not going to know what I'm talking about. Is it north of east? Is it east north? Is it something else? And so we're going to look at this, and 15 degrees north of east is different than 15 degrees east and north. And it's important, and when you think about the angle, you include the first word next to it. 15 degrees to the north, 15 degrees to the east. And we're going to see this is going to help us in having a baseline. We're going to go that 15 degrees north from. So here we're going north of east. Here we're going to go east of north. And this second thing that we have here is called a baseline. So let's look a little bit closer into a baseline. It's a reference point from which you describe an angle. So I went to 20 degrees north of what? It's going to be some sort of axis. It could be north, south, or it could be just the y-axis. There's a lot of different ways to name them. They could be positive y-axis, negative y-axis. So we'll see that. I'll have a couple different examples in here. So I went 20 degrees to north of what? I went 20 degrees north of the east. And so it's always going to be the last thing that you see that's going to be a baseline. And so I go east, and then I go 20 degrees in a northern direction from that east right here. I went 20 degrees north of what? In this case, the positive x-axis. So you don't have to always, it's not always north, east, you're not always using the compass rose. You could be just talking about the axis in math. Another thing, just going into the next section, just remember that this is a 90 degree in between this, 90, 180. This is going to be important because there's also multiple ways to describe a vector. I can say for this one, I can say it's 40 degrees to the east of my baseline, which is north, which is up. I could also describe this exact same line saying it's 50 degrees to the north or above this east. In this case, my baseline would be the east. So just remind yourself, the baseline, the last thing you see, 40 should be together, the baseline's right there, 50 degrees to the north of what? The baseline, which was east. So you start with east, you go up, in this case north, and here you start with north, and then you go east, that 40 degrees. So once again, tie that 40 to the east direction when you're thinking about these. Sometimes in math, we could also say, if we're talking about, an entire 360, and complete circle, we might just say from a 0 point. So you might see that. I'm not going to use it that often, but just don't forget 50 degrees angle would be from the 0 point right here all the way around would be 360. And so you could use that as well with the description. So here's your baseline. I've already talked a lot about that, so I'm going to kind of zip by this part. Let's get some practice. Go ahead and do these practice questions 6, 7, and 8. Once again, pause the video, get your answers, and then press play and see how you did. Okay, so this first one's going to be 15 degrees to the west of north of this baseline. Second one's going to be 20 degrees to the south of the baseline, which was west. So we're going 20 degrees south here. Here we're going, once again, it's the angle that I wrote here that I want you to go with, 50 degrees to the north of what? Of this east point right here. Okay, now just going the opposite way, and I'm going to show you kind of an easy way to go about these, and this could help you out, and because you're going to have to draw these and do a little bit more with them later on. So we have 30 degrees to the north of east. One way to go about these is to draw origin dot, which I did right there. So draw an origin dot, and then do the baseline first. Go east first. Draw an arrow tip. Every single line you have in this unit should have an arrow tip on it. We're dealing with vectors. So to go 30 degrees north of east, you have to go somewhat east and you have to go somewhat north. And so we're going to go north from that east. We're going to follow it backwards. Baseline, we got the origin dot, then we went east. And then from there, we're going to go north. And then from there, we're going to go ahead and we would just finish off. This is the resultant that I would have described, and I throw the 30 degrees closest to the origin dot. So that helps you place that 30 degrees. So once again, just follow me through this. We're going 25 degrees north of west, so we're going to go west first. We're going to draw origin dot, then we go west. Still want to show you the answer there. Origin dot, then we go west, and then we go north from the west. Then we finish off the triangle, and then we put that 25 degrees closest to this origin dot. So finish those off once again, and then check your work. Just make sure you're getting the same answers, and then you're going to be ready to move on to the next section. So I'm just going to go ahead and play out what these look like. And you should be checking your work, making sure you're getting the same answer. So So once again, we're describing this line. We're not actually describing the south or the east. It just happens to be that we go so far south, or in this case east, and so far south to be able to describe the line. The only line that really matters here is going to be this line that's darker. That's why I made it darker in these. And then we're not always going to use west. We might say negative x. So this is just so similar this would be similar to an x, and that's what that would look like. So that would be 10 degrees above the negative x axis. Okay, so the next section, finding a component of a vector, requires our previous bit of lesson, what we just went through. So you need to make sure that you understand that enough. Also, you need to know a little bit about trigonometry. We're going to go ahead and just remember, if you have an angle, when you go across, the side that is across is called the opposite. The longest side is the most famous side, the hypotenuse. And then the one that's not the opposite, or the one that's the side or adjacent means to the side, that's going to be the adjacent side. So I always go, biggest line is the hypotenuse every single time. I find the angle, and I go straight across, and that ends up being the opposite. And then the adjacent will be the other one. Now that changes. Notice how if I was describing this angle, the opposites were all the way across it. So be careful. When you solve for a certain side, it's not always going to be sine. It's not always going to be cosine. Some math classes, I think some teachers have said that, just if you're solving for the y-axis, it's always going to be sine, or it's always going to be cosine. It's not. You have to look at where the angle is, and if the angle's up here, the opposite's down here. If the angle's right here, the opposite's over here. Hypotenuse doesn't change. It will always be the longest side. So we go from there. Another thing, Pythagorean Theorem, in this unit, we're going to use Pythagorean Theorem a lot. A squared plus b squared equals c squared, but we're often not going to use it that way. We're going to go straight to c squared, or c, to solve for the hypotenuse, and c would equal to square root of a squared. We're going to go ahead and take the square root of both sides. We end up getting c equals a squared plus b squared. That's the most common form of this equation we're going to use. And then Sohcahtoa, remember your Sohcahtoa. It's on the equation sheet that we use in our class, but you only get these versions of it. So sine of an angle equals opposite of hypotenuse, tangent of an angle equals opposite of adjacent, cosine of an angle equals adjacent over hypotenuse. But they're not going to be the most common used. We're going to start with these, and these are on your equation sheet, but you have to remember we're going to be often solving for an opposite side or adjacent side, or later on we'll be solving for an angle itself. That would be the most common place where we can use inverse tangent. In honors, in CP, we're going to probably stick to just basic solving for these. In honors, I can write the questions differently, so you might have to use a tangent to solve for a side. But these are going to be the most common that we'll use. And just a reminder how you get this. If you multiply both sides by hypotenuse, that crosses out the hypotenuse, and the opposite equals that right there. So that's all you have to do, is just remember the math, how to do that, because you have this on your equation sheet, but you might have to get it to that on your own. So you need to know enough to do that, how to do that. With tangent, you have to inverse tangent both sides. So tan -1 of both sides, and that gets rid of this tangent. That gets rid of that, because inverse tangent of tangent, and then you end up getting that form right there, which we'll see a little bit more in the next unit. Okay, any vector that's not directly on an x or y axis has components, so we're going to go ahead and solve for components. We're going to look at this. What's the west component of 85 meters, 25 degrees north of south? So we started with the direction naming, how to draw that, but now we're going to go ahead and look at the overall. And if we're going and drawing an overall, I'm actually going to walk you through the basics of this. If I go ahead and go west first, and then I go north second, and then I go ahead and draw the overall the vector that I'm describing, and then I go ahead and put the 25 degrees closest to the origin dot. I have arrows all around, and then I can throw that 85 meters. This will always be the hypotenuse if it's next to an angle like this. So just remember that, always the hypotenuse if next to the angle. If it's either north or south, and or north or west or whatever, and there's no angle, then it might not be. It might just be a component. But anytime you see this, it will always be the hypotenuse. So we go through and we finish that off, and then we're going to have to solve. I can go 85 meters, 25 degrees north of west, or I can go west and north and get to the same ending spot. So when you're coming up with a component, you're trying to determine what can you do just on one axis to get to a position where you can do one more direction and end up in the same spot. 85, so components make up the overall. They lay directly on the x and y axis. Components can take you to the same ending points. Once again, take a look, start to finish, or you can go this, and you can get to the same finish finish spot. The resulting vector is always directed from start to finish again. There's gonna be a contradicting arrow when you look at this. You see, you go left, you go up, or you can go straight west and north at the same time at a 25-degree angle and get to the exact same spot. But watch this, the resultant should be ending in the same spot that your last direction. So I went that way, then I went that way, I ended there, or I can do this instead and end there. That's getting a little sloppy, but hopefully you get the gist of what I'm trying to say. It's always going to be less. The either component, you'll never be, you can tell if you have a big error. If your hypotenuse is 85 and you somehow solved for the west side and you got 90, you know you did something wrong. Neither of these are ever going to be bigger than the hypotenuse. So it's something just to watch out for. So let's go and do the math, or let me show you walking backwards. Start with the origin dot. So you can start with an origin dot, then you go west first. That's the baseline first. The dot is always has a baseline coming out of it. Then you go north from that dot, and then you draw the overall line from start to finish. Once again, arrow tip away from the beginning. Throw that 25, well, throw the number on the overall of the hypotenuse and throw the angle closest to the origin dot, and now you have something you can solve for to solve for the north or west component. That's what we're going to do for the rest of this section. Calculator time. This is very important. Take a look. This thing that says degrees, you have to hit mode on your calculator. And then after you go to that, calculators, I know when mine resets, goes into radians, you got to switch it to degrees. So you have to be in degrees, or you're going to wonder why you're getting a different answer than I am. You're going to check this all the time. It's going to happen over and over and over. If you don't check that you're in degrees, your math class will maybe take you into radians, and you get an answer wrong. So make sure you're always in degrees when you're typing in sine, cosine, tangent, inverse of any. If you're typing in any of these trig functions, you need to make sure you're in degrees. Anything else, you're fine. But those trig functions, you need to make sure you're in degrees. So very important. You're going to find that might mess you up once or twice because you forgot to do that. So what's the west component of 85 meters, 25 degrees north of west? I went ahead and drew out this triangle earlier, but we're looking for the west component. And this is where you have to remember, okay, my angle is right here. If you drew your angle wrong, if you drew your triangle wrong, you didn't put your angle closest to the origin dot, you might not have this being the adjacent side. And so I have the adjacent side, I also have the hypotenuse, and that's going to lead you to cosine. But I'm going to use more common. I'm going to rearrange that. Adjacent equals cosine times hypotenuse. Plug in the numbers. And I'm going to get a final answer when I type this in right. If my calculator is in degrees, so I'm going to get 77 meters. But I'm just describing west. So this is very important here. I took 85 meters, 25 degrees north of west, and I just broke out one part of this. That's all I did. So it's important. And another thing that's very important to do, if you don't draw arrow tips, you're going to think, oh, I'm trying to solve for the west side. This is the west side over here. It's not. This side is facing up. This side is north. So it's very important to have arrow tips because you're solving for the side that has arrow tip facing west. Not the west side, but the side that has the arrow tip facing west. Make sure you're always drawing the arrow tips on every single one of your triangles. Look back at anything else you drew and see, make sure every single arrow tip should be drawn in on these lines. Okay, what's the north component of 85 meters, 25 degrees north of west? Well, here we have the opposite side, and we have the hypotenuse. Once again, the opposite, it opens up. This 25 opens up to the opposite side. And that is the arrow facing north. I'm asked for the north component, the arrow facing north. And then we can go ahead and use the trig function that has opposite and hypotenuse in it, and that's going to be sine. But we'll use it, we'll rearrange it and get to this form. And we'll plug in our numbers. And then we'll get our answer, and we'll leave that direction because now we just broke that 85 meters, 25 degrees north of west into two components. If I went ahead and went back to my last answer, if I went 77 meters west first, and then I finished off and went 36 meters north, I would end in the exact same spot as if I went 85 meters, 25 degrees north or west. Okay, so here's your problem set. You can work this problem set, and then check your answers afterwards. And so just come in and then use this video, pause it, do the work, and then come back.